900 light-years away, there's an unseen antimatter factory churning out high-energy positrons, tiny particles of antimatter that are streaming through the cosmos and colliding with our planet. For much of history, we didn't know this strange source existed. Most of the positrons bombarding us went completely undetected, instead getting absorbed in our planet's atmosphere. It wasn't until we started looking from beyond the bounds of our planet that we noticed them. In 2008, the PAMELA satellite orbiting Earth was activated to hunt for cosmic rays, a cutting-edge detector scanning the void for charged particles racing through space. What did it find? An unexpected surge of positrons. The presence of these subatomic particles was to be expected, but not in the numbers they were finding. Such was the sheer volume of positrons being detected that the usual sources like natural radioactive decay and cosmic rays no longer offered a sufficient explanation. So where were they coming from? We've only recently been able to trace the culprit of this cosmic antimatter shower, and it all comes down to another high-energy discovery. A strange gamma-ray haze named Monogem, first glimpsed in the 1970s. What is this mysterious source of gamma radiation? And what does it have to do with the unusual abundance of high-energy positrons hitting our planet? Up in our night sky, nestled in the Monoceros constellation, in the northern celestial hemisphere, there is something peculiar going on. In 1971, NASA's Uhuru X-ray satellite, the first dedicated to scanning the heavens in X-rays, identified an extended glow of soft X-ray emission. But with the technology available at the time, the best it could do was trace its origin to this wider region of our Milky Way. So the radiation's ultimate source remained hidden among the stars for years. Nevertheless, it was given a name. Monogem, coined in the late 1970s by astronomers studying its diffuse ring-like structure, a blend of Monoceros, the unicorn constellation where it resides, and Geminga, evoking a similar enigmatic source nearby. Monogem also carries an air of mystery in its naming, suggesting a ghostly remnant that almost isn't there, a fitting title for an X-ray haze with an unknown heart. It wasn't until 1980 when astronomers finally had their big break. They managed to identify a faint radio signal from within Monogem using ground-based telescopes like the Arecibo Observatory. This meant, although its exact nature remained elusive, they could narrow down their search area and were getting closer to uncovering Monogem's hiding place. But it didn't answer the big question. What is it? As astronomers could still only offer vague guesses about the true nature of the source. That was until 1992, when they had another lucky break. Two separate missions identified radiation coming from Monogem, and they weren't constant signals, but pulses. The first of these discoveries was made with the Rosat X-ray Telescope, a German-led mission that mapped the X-ray sky with unprecedented detail. Rosat was the first to identify pulses in the X-ray signal coming from Monogem, and soon after, they were also confirmed in the gamma wavelengths by the Compton Gamma-ray Observatory, a NASA satellite carrying instruments to probe the most energetic light in the universe. Not only did these complementary observations demonstrate that the X-rays and the gamma rays were both coming from Monogem, but for the first time, they revealed what Monogem was. With a period of 0.385 seconds, flashing as it spins around its axis a little more than 2.6 times per second, Monogem behaved like a pulsar. A pulsar is a type of neutron star that spins rapidly emitting beams of radiation that sweep across space like a cosmic lighthouse. From across the galaxy, most pulsars appear to flash in radio waves, anywhere from a few times a minute to as fast as 700 times per second. And at this point in the early 90s, they were incredibly rare. You see, before Rosat and Compton, only a handful of high-energy gamma-ray pulsars had ever been identified, the Crab and Vela pulsars. And Crab and Vela were different to Monogem in a couple of key ways. First, in addition to gamma rays, both of these pulsars also produced radio waves and were therefore visible using radio telescopes. So if Monogem was a pulsar, then it would be one of the few where the radio emissions were faint, almost drowned out, only emitting enough radiation to be seen prominently in the gamma and X-ray wavelengths. And second, Crab and Vela are surrounded by their respective nebulae, remnants from when they were created from supernova explosions. But Monogem's nebula was vast and diffuse, a 25-degree wide ring of glowing gas, unlike the compact clouds around others. So why is Monogem, this powerful source of gamma rays, so subtle in radio waves compared to its kin? Where does its enormous ring come from? Or could it be a different type of object altogether? Well, the answer to the first question is, in part, because its emissions are shaped by extreme conditions due to the limitations of early technology and our evolving understanding of the radio emissions from such stellar remnants. You see, while radio pulses can emit radio waves across a wide bandwidth from as low as 20 megahertz to above 100 gigahertz, spanning much of the radio spectrum, not all of these frequencies travel well through space. Even though we've known since the 1980s that radio pulsars often peak between 400 to 1400 megahertz, where they are intrinsically brightest, things like the interstellar medium, galactic background noise, and scattering effects mean that lower frequencies are scattered as they make their way across space, resulting in broadened pulses that are more difficult to detect. Because those radio signals can be smeared, many radio telescopes focused on higher frequencies, instead confining themselves to searching for signals above 1 gigahertz. This would have been fine had Monogem behaved as expected for one of its kind. Since it did not, it took until 1995 for scientists to realize what was happening. Observations from the Green Bank telescope identified weak but distinct pulses from Monogem, using sensitive arrays tuned to lower frequencies. The faint radio pulses came in around 400 megahertz, which explains why previous radio searches for Monogem had been inconsistent. Turns out Monogem wasn't truly silent and had been sending us signals. We just weren't tuned to the right channel. That same era, theorists proposed that another reason Monogem appeared radio faint might be its age and magnetic field. Models showed that as pulsars age, their radio emissions could weaken or shift frequencies absorbed within the pulsar's magnetosphere, leaving only faint traces at certain bands. This would effectively make it quieter at the higher radio bands that most telescopes targeted. Confirming Monogem was a pulsar, and specifically a gamma-ray pulsar, was a big deal. In fact, over 90% of its output is in the gamma range, making it one of the brightest gamma-ray sources in our local stellar neighborhood. It is, as it turns out, all that's left after a star, several times more massive than our Sun, exploded about 110,000 years ago. But its subtle radio presence and its oversized nebula weren't the only unusual things about this pulsar. When astronomers compared a series of observations from the Hubble Space Telescope and ground-based optical surveys with X-ray data from Chandra. They found that Monogem was moving. Not only that, it was traveling at an unusually high speed of around 0.15 arcseconds per year. As a reminder, an arcsecond is a very small unit of angular measurement, used when we need more precise measurements than a degree would allow. Within each arc degree, there are 60 arc minutes, and within each arc minute are 60 arc seconds. These arc seconds are a common unit used in astronomy to talk about the movement of objects across the sky from our perspective on Earth. If you were to draw a circle around the orbit of the Moon around the Earth, there would be 360 degrees around that circular path. So at any given time of day or night, assuming nothing is blocking your view of the horizon, you can see about 180 degrees of the sky, and from the horizon to the zenith, the top of the sky is 90 degrees. If you hold out your little finger at arm's length and close one eye, the tip of your little finger covers about 1 degree of the sky, roughly. Next time you're outside, on a clear night, try this and see if your little finger can cover the moon. It should, because the moon takes up only about half of a degree or about 31 arc minutes in the night sky. Monogem traveling 0.15 arc seconds across our sky each year may not sound like a lot, but from our perspective on Earth, the typical star only moves a few thousandths of an arc second per year. Yet despite being 900 light-years from us, Monogem will travel 20 arc minutes, nearly the equivalent to the apparent width of the Moon, across our sky in just over 10,000 years. In other words, this stellar corpse is racing through the galaxy at nearly 180 kilometers per second. Heading toward the edge of Monoceros and into neighboring constellations, and at its current rate of motion, Monogem will remain in its namesake for another 250,000 years. But it may need a new label after that. However, this mysterious pulsar gets stranger still. It's its vast speed that helps produce another feature that scientists were about to discover. As it hurtles through space, Monogem carves out a bow-shock nebula, a glowing arc of X-rays stretching millions of kilometers ahead. As I discussed earlier, despite the fact that this fast-moving pulsar has faint radio emissions, it certainly isn't quiet in the gamma-ray and X-ray wavelengths. In 2001, NASA's Chandra X-ray Observatory was launched to unveil the high-energy universe, and 2 years later, a team uncovered this comet-like bow-shock in front of Monogem. Its shape and brightness are partly explained by the shockwave created by Monogem's motion through space and its rotation as a pulsar. But they are also revealing of another attribute: Monogem's colossal mass. Measuring only about 20 to 30 kilometers across, Monogem is extremely dense, containing about 1.4 times the mass of our Sun. To put that in perspective, if you had a teaspoon of neutron star material, it would weigh about 5 billion tons, as much as 12,000 Empire State Buildings. As this dense, high-mass object races forward through the low-density interstellar medium, just 0.1 to 0.3 atoms per cubic centimeter, it compresses the interstellar medium and its own embedded magnetic field by a factor of 3. Meanwhile, the incessant spinning of the neutron star creates an environment where electrons and their antimatter counterparts, called positrons, can be accelerated to extreme energies, powerful enough to emit high-energy gamma rays. While most of these electrons are seen in the gamma radiation that escapes from the pulsar, some get trapped and spiral within this enhanced magnetic field. In these images, From a computer model, the bow shock appears as a curved front, like the prow of a ship slicing through ocean waves. Only this ship is denser than our sun, and the wake is made up of extremely high-energy X-rays. But the final piece of the monogem puzzle wasn't discovered until 2010, its extended gamma-ray halo. Taking the form of a diffuse glow of high-energy particles extending 10 parsecs wide, it turned out to be what we call a TV halo, a region where cosmic rays are trapped and re-accelerated. This type of halo is created from the wind of charged particles that emanates from a pulsar's magnetic poles. The plasma, made of electrons and positrons, accelerated to near light speed, surrounds the pulsar, creating a nebula of high-energy particles that give off strong gamma-ray emissions. With the confirmation that monogem did have this halo, its identity as a major cosmic ray accelerator could finally be confirmed. But Fermi and HERC went even further. In addition to imaging monogem, these observatories also looked at similar pulsars, and by comparing them, astronomers uncovered another possible explanation for the variability in radio and gamma emissions. On the surface, these pulsars seem quite similar. They are both about 100,000 years old, and they spin about 2 to 5 times per second. However, as you know, monogem is seen primarily in gamma-ray pulses with weaker radio emissions. By contrast, some nearby pulses are brighter in radio and fainter in gamma rays. How could these pulses be so similar, yet so vastly different in how we see them? The answer may be as simple as how each of these pulses are oriented, relative to our observation from Earth. Astronomers believe that these images of monogem and its kin have revealed their spin axes and uncovered a reason for why radio and gamma-ray pulses may be present or absent on different pulsars. Like our own magnetic field around Earth, these pulsars have magnetic poles close to their spin poles. These poles are where the beams of pulsing radio emissions come from. You could try to model this if you skewer a little foam ball right down the middle. The foam ball is a pulsar, and the radio beams coming from the poles are represented by the wooden skewer coming out both ends. If you spin the ball around the skewer like a spin axis, you create an equator around the middle. To illustrate the gamma-ray source along the spin equator, called the outer gap, you could cut a hole in a paper plate and squeeze it over the foam ball. Now you've got yourself a disk of gamma rays beaming out from the equator in every direction. With monogem, the edge of the paper plate is angled toward us, meaning the gamma rays are heading to Earth. But for other pulsars, their relative position to us is at a different angle, as if looking at the flat surface of the plate. The gamma rays are moving perpendicular to our line of sight, therefore missing Earth. Let's look again at the images of monogem, alongside artist illustrations of what astronomers believe the pulsar wind halos look like. In the image of a radio-bright pulsar, the long trailing tails represent the radio jets emanating from its poles and the skewer coming out of both ends. Only instead of being straight like a wooden skewer, it is moving so fast through space that these jets appear bent backward, trailing behind as the pulsar moves through space. Now look at the image of monogem. Here, the curved bow shock in front is the compressed magnetic field, with gamma emissions dominating the view. So when astronomers look at monogem, they see powerful gamma-ray emissions from the equatorial regions, but the radio jets are misaligned and remain fainter. And when they look at radio-dominant pulsars, the opposite happens. The radio jets are pointed more toward our planet, while the gamma-ray source at the equator glances past Earth. Sometimes the most simple explanation is the correct one. And that finally brings us back to the decades-long mystery of an unusual abundance of antimatter bombarding our planet. For over a decade, the Alpha Magnetic Spectrometer, or AMS-02, has been attached to the International Space Station, collecting information on antimatter, dark matter, and cosmic ray sources. As a reminder, cosmic rays are energetic particles, fragments of atoms, that travel through space at nearly the speed of light. These can be made by the sun, by supernova explosions, or other cosmic means. And in 2019, updated results from AMS-02 were announced. The detector had recorded millions of positrons, the most precise sample of cosmic ray positron data ever collected, extending the world's total cosmic ray positron data by orders of magnitude. For years, many astronomers and physicists hoped that this excess antimatter may be the byproduct of dark matter annihilation, offering possible clues about this mysterious substance. After all, dark matter could make up around 85% of the universe's mass, and yet we still don't know what it is. Like regular matter, dark matter holds mass and exerts gravity, but it doesn't seem to absorb, reflect, or interact with light, at least not in a way we can detect. Some theorize that dark matter may be made of exotic particles like axions or WIMPs. Whatever it is, scientists had high hopes that the overabundance of antimatter being detected aboard the ISS may hold clues about dark matter's true nature, perhaps from self-annihilating particles in dense halos. Unfortunately, they've been left disappointed. The more scientists dig into the data, the clearer it's becoming. The most likely source of these positrons may actually be pulsars. Astrophysicists had long suspected this, but until 2017, there simply wasn't conclusive proof. It was the High-Altitude Water-Cherenkov Gamma-ray Observatory, or HAWC, that finally added evidence to this hypothesis. Extended TV emission was identified surrounding monogem with energies trillions of times more than visible light, from 1 to 100 trillion electron volts. The sort of radiation usually produced by positrons and electrons scattering off background light. This was the first real observational evidence pointing to a pulsar as a potential source. Pulsars naturally surround themselves with a haze of both electrons and their positron counterparts as a result of the star's intense magnetic field. This intense magnetic field pulls particles from the pulsar's surface and accelerates them to near the speed of light. Scientists think that these accelerated positrons and electrons are then colliding with low-energy photons, boosting the light to higher energies through inverse Compton scattering, which then radiates as the gamma-ray halo observed. But based on the size of the halo the HAWC team saw, monogem's positrons would have to diffuse slowly to remain trapped, raising questions about whether they could reach our planet. And so they believed that the excess positrons must have a more exotic source. That was, until stunning new information was uncovered in recent years thanks to a team analyzing Fermi data. Using over a decade of gamma-ray data about monogem acquired from Fermi's Large Area Telescope, which is able to observe lower energy light than the HAWC Gamma-ray Observatory, the team was able to subtract out all other gamma-ray sources to reveal a spectacular glow coming from monogem, much, much bigger than what scientists had ever seen before. This vast, elongated halo of glowing gamma rays at energies around 10 billion electron volts spanned 15 degrees of the sky, comparable to the span of Orion's belt. And that's not all. The glow of gamma radiation is even bigger at lower energies. If we could see it with the naked eye, Monogem's gamma glow would loom large in our sky, covering an area 30 times bigger than the full moon. With this new information, astrophysicists found that the size of Monogem's halo meant this one pulsar alone could be responsible for as much as 15% of the excess positrons detected near Earth. From there, it's no stretch to imagine that other nearby pulsars are the most likely culprit for the remaining antimatter abundance we found. This explanation may not have solved the mystery of dark matter, but it is certainly a magnificent revelation. It was in 1967 that the first pulsar was discovered, back when people thought those regular signals could be the work of extraterrestrial life. Perhaps beacons from advanced civilizations harnessing neutron stars. In the nearly 60 years that have passed since, we have found thousands of pulsars, and our understanding of these neutron stars has grown with every one. And since Monogem was identified as a gamma-ray pulsar in the 1990s, we've now spotted over 300 thanks to NASA's Fermi mission. But given Monogem's track record of defying expectations and furthering science, I like to think that this particular pulsar has more secrets still to reveal. Deep within the quantum realm of these spinning corpses, where magnetic fields reach quadrillions of times Earth's, pair production erupts from the vacuum itself. Electrons and positrons born from pure energy, a process governed by quantum electrodynamics, blurring the line between matter and nothingness. This antimatter factory challenges the cosmic baryon asymmetry, the puzzle of why matter dominates over antimatter in our universe, born from the Big Bang's fiery crucible. Could such pulsars hint at hidden symmetries broken in the early cosmos, or even loops in time where annihilation rewinds? Recent models speculate that in extreme fields, virtual particles become real, fueling jets that could seed quantum fluctuations akin to those in black hole horizons. Imagine if a rogue pulsar wandered too close. Its positron stream could ignite atmospheric cascades, unleashing energies rivaling particle accelerators, probing physics beyond the standard model. Yet in this revelation lies a thread of fear. Antimatter's touch means total annihilation, converting mass to pure gamma fury, a reminder of the universe's indifferent power. But woven with awe, for in Monogem's pulse beats the heart of a dead star, alive with radiation, illuminating the void and whispering secrets of creation and destruction. Emerging discoveries from 2024 and 2025, like the AMS-02 upgrades, capturing record-breaking positron energies, and HWC's detection of even more extended halos, suggest pulsars like Monogem dominate the flux, dismissing dark matter annihilation with fresh data. Yet, lingering anomalies hint at hybrid sources, perhaps micro-black holes evaporating via Hawking radiation, spewing positrons as they fade, or even speculative wormholes linking distant realms, channeling antimatter across space-time. In the galactic dance, where black holes devour and spit relativistic jets, Monogem stands as a sentinel, its bull shock a shield against the interstellar wind, carving paths for positrons to journey to our world. Quantum mechanics reigns here, with Heisenberg uncertainties amplified in neutron star crusts, where superfluid neutrons flow without friction, and quark matter may lurk in cores denser than atomic nuclei. This bizarre object forces us to confront reality's fragility. One positron meeting an electron erases both in a flash, mirroring perhaps simulation glitches in a coded universe. where base reality leaks through cosmic rays. Trending theories tie this to fast radio bursts, enigmatic signals from magnetars, cousins to pulsars, potentially alien megastructures or natural amplifiers of quantum noise. In 2025, with JWST peering into supernova remnants, we glimpse infant pulsars, birthing antimatter clouds, challenging inflation models, and hinting at multiverses where antimatter worlds mirror our own. The emotional weight crushes, awe at the universe's ingenuity, fear of its destructive potential, wonder at how a distant explosion 110,000 years ago now rains antimatter upon us, altering our skies invisibly. Philosophically, it underscores our insignificance yet connectivity. Every positron a messenger from stellar death, carrying echoes of quantum birth. As we decode Monogem's rhythm, we edge closer to unveiling cosmic secrets, from time's arrow to reality's fabric, in a thriller where the stakes are existence itself. But the story deepens with recent breakthroughs. In February 2025, a paper disclosed catalogued pulsars, including Monogem and Geminga, as dominant contributors to the galactic positron flux, consolidating models where pulsar wind nebulae accelerate antimatter to earthbound speeds. This shatters earlier doubts, with multifaceted reasoning over chronological data from Fermi and AMS, revealing how diffusion barriers are overcome in turbulent magnetic fields. Shocking still, 2024 observations of the most energetic cosmic ray electrons and positrons ever at petavolt scales suggest pulsar origins over dark matter, with implications for quantum gravity. Could these positrons probe string theory dimensions or hint at simulation theory artifacts? In the haze of Monogem's halo, we see not just radiation, but a canvas of emerging truths, where black holes' shadows loom, and alien life might harness such energies for interstellar signals. The fear intensifies. If antimatter fluxes rise from galactic events, could they trigger geomagnetic disruptions, unleashing auroras of annihilation? Yet the wonder prevails, as each pulse reveals philosophical depths, a universe balanced on matter's edge, where one bizarre object bombards us with reminders of our quantum origins. Expanding on the quantum intensity in the pulsar's magnetosphere, fields exceed the Schwinger limit, where vacuum polarization spawns particle pairs spontaneously, a quantum electrodynamic marvel verified in lab analogues but writ large in space. This ties to black hole analogues, where event horizons mimic pulsar poles, suggesting unified theories blending general relativity with quantum fields. Speculative but grounded, recent papers propose positrons